Assalamu alaikum everyone. In the name of Allah, the most beneficial and the most merciful. I am Maheen Shehzad from Department of Chemistry at University of Management and Technology, Sialkot, and I am here to present my review article on the topic Advanced Material Chemistry in Electronics, which is done under the supervision of Dr. Hamad Majid. First of all, I'll discuss about abstract. Advanced material chemistry is integral to advancing the development of cutting edge and effective electronic devices. This article explores three pivotal applications and material chemistry in the field of electronics: lithium ion batteries, perovskite solar cells, and semiconductors. The operational principles, strengths, and weaknesses of these devices are elucidated. Moreover, we evaluate recent progress and potential future developments in these technologies, highlighting both the challenges and opportunities for ongoing improvement. This article highlights that material chemistry serves as a critical determinant for innovating and optimizing electronic devices, underscoring the imperative for ongoing research and collaborative efforts to surmount existing challenges and attain the desired levels of performance and sustainability. Introduction to Advanced Material Chemistry. Material chemistry is a specialized field of chemistry which is focused on preparing, characterizing, and comprehending substances or systems intended for specific practical purposes. Advanced materials encompass the creation of new materials or the modification of an existing one, boasting superior features that can surpass those found in traditional materials. A material is characterized by the properties that grant it potential for a specific application, whether it's structural, as in the case of building materials, or functional for materials used in crafting devices, or biological, catering to biomedical applications. It is recognized that the act of synthesizing a new chemical substance, whether on a nano or microscopic level, does not categorize it as material chemistry, but rather aligns it within the domain of chemical synthesis. To be classified as material chemistry, an element related to application, function, or design must be present in that material. First of all, now we'll look at this topic: lithium ion batteries. Lithium ion batteries are also known as technological wonders and are now increasingly replacing the traditional lead acid batteries. The success of lithium ion batteries lies in their low cost and high energy density. Cost and performance improvement has also been attributed to cell chemistry and construction. New materials have been adopted to construct positive and negative electrodes, and energy content has also been increased. Construction of lithium ion batteries. It consists of cathode and anode. Lithium cobalt oxide batteries comprises about 60% cobalt by mass, which makes up the cathode and is highly expensive. In order to decrease the cost, cobalt mass is reduced, such as in NMC 811 battery, in which only about 6% cobalt is present by mass, therefore making it cost effective. The low cobalt content means that the raw material cost is less. Working principle. Here, we will discuss the working principle of lithium nickel oxide batteries, which are widely used in electric cars such as Tesla and in cell phone by tech giants like Panasonic, Samsung, and Apple. In its pure form, lithium is very reactive. However, when it's a part of metal oxide, it is quite stable. When a lithium atom is separated, it forms a lithium ion and an electron. Electricity can be produced from lithium metal oxide by separating lithium atoms from lithium metal oxide and guiding the electrons through an external circuit. When lithium ion battery is charging or discharging, an electron and an ion leave one electrode and arrive at other electrode at the same time. Cathode. In case of lithium nickel oxide, Nickel and oxygen are strongly bonded to each other and borrow an electron from lithium, as nickel oxide has greater tendency to borrow electrons, and lithium has electrons which are readily available. When battery is connected to a source, lithium ions are liberated from lithium nickel oxide crystal to the electrolyte solution. As soon as ions are liberated, electrons are also liberated from cathode and they move towards anode. The stripping away of electrons makes the nickel oxide crystal electronegative. Each electron taken from cathode, the cathode becomes more electronegative, hence more voltage is required to separate further electrons as cathode holds the remaining electrons more tightly. Electrolyte solution. As each electron strips from nickel oxide cathode, a positively charged lithium ion is released and flows out of the layered structure into the electrolyte solution, wandering towards the node by diffusion. The electrolyte solution is made of solvents, but it doesn't react with positive lithium ion. However, the solvent is attracted with the positive charge of lithium ion and is surrounded it. This forms a solvation cell. The ions float freely through the solvent with the air of solvation cell. In this way, a cloud of ions is released in the electrolyte solution by diffusion. The electrolyte solution can conduct ions, but it won't conduct electrons. A separator is also present in the electrolyte solution and it is porous, allowing only lithium ions to pass through. This separator also acts as a shield, preventing both cathode and anode from contact, otherwise, the battery will short out. The electrolyte contains lithium salt. When the salt is dissolved in a solvent pulls the salt apart, leaving behind positive and negative ions, with solvation cells hence maintaining a neutral charge. Anode. At anode, the electrolyte solution is depleted of lithium ions. The buildup of lithium ions at cathode and depletion at anode is called concentration gradient. At anode, lithium, solvent, and the additive are reacting with the shells of graphite particles to form a protective film on graphite particles. Vinylene carbonate is present as an additive, which helps this layer to form into a stable surface that extends battery life to thousands of cycles. This is known as solid electrolyte interface. It is a solid layer and lithium ions pass through this layer. When electrons from cathode move towards anode, they bond to lithium ions, thus forming lithium atoms. These lithium atoms sit in the layers of graphene and make up the graphite. Lithium atoms are held in place by electrostatic forces. The battery is now fully charged and is highly reactive. Lithium atoms are stored in graphite. Discharging of battery. Lithium has electrons that can be removed readily, but nowhere to go as electrolyte solution can't conduct electrons and graphite being stable won't conduct electrons. Therefore, these electrons can escape to cathode. One electrolyte will accept the positive lithium ion by removing a positive lithium ion from solution at cathode. When opening an electrical pathway between cathode and anode, imbalance is sensed by all electrons. Electrons in outer shell of lithium leave readily, while at cathode, the nickel oxide crystal structure is electronegative and seeking those electrons. During discharge, the lithium at anode releases an electron which is taken up by nickel oxide crystal structure, which combines it with lithium ion. The lithium atom that lost its electron is released into the electrolyte solution as positive lithium ion. Hence, charge is only carried for a short fraction of a second. In the beginning, there is substantial energy balance, which is about 4.2 volts. But as lithium migrates from anode towards the cathode, the charge imbalance diminishes, which is also accompanied by decrease in voltage. The discharge cycle concludes at 3 volts, and the system is now ready for recharging. We can also see the diagram of lithium-ion battery, in which both cathode and anode are present along with a separator in the electrolyte solution, and the battery is also connected to a power source. Lithium-ion batteries in Tesla. In all lithium-ion batteries, anode is made up of graphite, and electrolytes are made up of lithium ion. But the material for cathode varies widely. The main cathodes which are used in Tesla cars are nickel cobalt aluminium, also known as NCA, or nickel cobalt manganese, also known as NCM. Tesla is currently engaged in efforts to enhance the nickel content while decreasing the cobalt content in its batteries to make it cost effective and to improve energy density, enabling the storage of significant amounts of energy so longer ranges can be achieved. A standard Tesla cell has voltage in between 3 and 4.2 volts. A large number of Tesla cells are connected in series to form a module. About 16 modules are connected to form a battery pack in Tesla car. Lithium ion cells generate substantial heat during operation, and Tesla addresses these challenges by employing a glycol based cooling system, concurrently implementing voltage protection measures to balance so that all the cells which are present in the battery charge and discharge equally. If only a large cell was employed instead of many small lithium based cells, then it would put a lot of strain during high power demands, resulting in premature cell death. The current achieved number of discharge cycles of lithium ion batteries is 3000 and is expected to increase to about 1000 cycles, which means that car batteries won't need any replacing for about 25 years. The second topic is perovskite solar cells. Perovskite solar cells are a type of cells that use perovskite structured compound as a light absorbing layer. Perovskite structure compound have the general formula ABH3, where A and B are cations and X is an anion. These compounds can be made from various elements or molecules and can have different optical and electric properties depending on their composition. Perovskite is generally a calcium titanium oxide mineral comprising of calcium titanate with the chemical formula CaTiO3. Manufacturing of perovskite solar cells. The first step is perovskite material synthesis. It will serve as a light absorbing layer. Typically, this step involves mixing lead halide salts such as lead iodide with organic cations such as methyl ammonium iodide to create the desired perovskite compound. Electron and hole transport materials. The electron transport layer, also known as ETL, and the hole transport layer, known as HTL, materials are prepared here. Common electron transport layer materials include titanium dioxide or zinc oxide, and typical hole transport layer includes organic hole transporting materials such as pyrometad. Substrate preparation, cleaning and coating. The chosen substrate, usually glass or flexible material, is cleaned and coated with a transparent conductive electrode such as indium tin oxide or fluorine doped tin oxide. Layer deposition. Deposition of ETL. The electron transport layer material is deposited on the transparent conductive electrode coated substrate. This can be achieved through techniques like spin coating or spray coating. Deposition of perovskite layer. The perovskite substance material is deposited onto the electron transport layer. This can be done by using different techniques like spin coating, doctoral blading, or vacuum deposition. However, care must be taken to ensure a uniform and high quality perovskite layer. Deposition of hole transport layer. The HTL material is deposited on the top of perovskite layer. This is typically done through spin coating. Metal electrode deposition. A metal electrode, which is usually made of materials like gold or silver, is deposited on a hole transport layer to help collect the holes which are generated in the perovskite layer, encapsulating and sealing. Protective layers. Perovskite solar cells are highly sensitive to environmental factors, so they are encapsulated or sealed with protective materials to prevent moisture and oxygen from degrading the perovskite layer. Electrical cords and wiring. Electrical connections are made to transport the conductive electrode and the metal electrode. These connections lead to an external circuit for collecting and utilizing the generated electrical energy. Quality control and characterization. The manufactured perovskite solar cells undergo rigorous testing to ensure that they meet the performance standards. Module assembly. For practical applications, individual perovskite solar cells are assembled into modules by connecting them in series or in parallel configuration, depending on the desired voltage and current output. Construction of perovskite solar cells. Substrate. In perovskite solar cells, typically the substrate serves as a foundation material and it is composed of different materials such as glass, plastic, or alternative transparent and flexible substrates depending on the specific application. Transport conductive electrode. A transport conductive electrode is deposited onto the substrate. This layer permits incoming sunlight to penetrate while aiding the capture of electrical current produced by the solar cell. Common material for TCEs include indium tin oxide, also or alternative conductive materials like fluorine-doped tin oxide. Electron transport layer. The ETL is a vital component that enhances the mobility of electrons within the solar cell. It plays a crucial role in transporting electrons from the perovskite layer to the electrode. Materials like titanium dioxide and zinc oxide are used as ETL. Perovskite absorber layer. This layer is the heart of the perovskite solar cell, where sunlight is absorbed and electron-hole pairs are generated. Perovskite materials with specific composition are carefully deposited onto the ETL. Methyl ammonium lead iodide is a frequently employed material in perovskite applications. Hole transport layer. The hole transport layer is another layer which is responsible for facilitating the efficient extraction of positively charged holes which are created within the perovskite layer. When it absorbs sunlight, organic hole transporting materials like spirometall are frequently employed as the HTL. Metal electrode, which is made up of materials such as gold or silver, is applied on the top of hole transport layer. This electrode is largely responsible for collecting the positive charge carriers, which are holes, which are generated within the perovskite layer. Different types of perovskite solar cells. The perovskite solar cells are categorized based on whether the incident light rays are initially encountered by the transport material on the external regions, be it electrons or holes. So they are of two types, regular NIP structures and inverted NIP structures. The NIP and PIN structures are further classified as mesoscopic structures, which has a mesoporous perovskite layer, and planar structure, which incorporates all planar layers. Regular NIP structure. In the NIP configuration of perovskite solar cells, the initial deposition involves the electron ETL, which is succeeded by HTL. In this perovskite solar cell type, the sunlight is first encountered by electron transport layer. The standard NIP perovskite solar cell structure is available in two architectures, NIP mesoscopic configuration and NIP planar configuration. In the NIP mesoscopic arrangement, a mesoporous metal oxide comprising of perovskite is positioned between ETL and HTL. The cathode is transparent glass and a metallic cap serves as the anode. NIP planar configuration. It does not have the mesoporous metal oxide layer. Within the NIP planar configuration, the placement of perovskite light harvesting layer occurs between the ETL and HTL. The effectiveness of planar NIP can also be enhanced by managing the interfaces among the different layers within the planar structure of a perovskite solar cell. NIP planar perovskite solar cells showcase elevated open circuit voltage and short circuit current density in contrast to the mesoscopic NIP structure. A significant limitation of planar NIP perovskite solar cells is the presence of correct density voltage hysteresis. The second type is inverted PIN structure. In the inverted PIN planar structure of perovskite solar cells, the initial deposition is of the HTL, and the incident light first interacts with HTL before reaching the ETL. Mesoscopic inverted PIN perovskite solar cells are made by organic, inorganic, and oxide HDL materials. The planar inverted PIN perovskite solar cell structures provide benefits such as low temperature processing, high efficiency, and minimal hysteresis behavior. Here, the diagram is given for all the types of perovskite cells. Working of perovskite solar cells. Light absorption. Perovskite solar cells consist of a thin layer of perovskite material which is designed to efficiently absorb sunlight. When sunlight strikes the perovskite layer, it excites the electrons in the material. Generation of electron hole pairs. The absorbed photons from the sunlight provide enough energy to the electrons in the perovskite material, causing them to move to higher energy state. This mechanism generates electron hole pairs, wherein an electron is released from its position, creating a positively charged hole. Charge separation. An internal electric field within the perovskite material causes the separated electrons in holes to move in opposite direction. Electrons are directed towards the electron transport layer, while the positively charged holes migrate to the hole transport layer, also known as HTL. Electric current generation. As the separated charge carriers move, they create an electric current. Electrons flow through the ETL and are collected at the transparent conductive electrode, which holes move through the HTL and collected at metal electrode. The flow of charge carriers constitute the electrical output of the solar cell. Realization of electricity. The electrical current generated within the perovskite solar cell can be directed to an external circuit where it can power various electrical devices or be stored in batteries for later use. Continuous energy conversion. As long as sunlight continues to illuminate the perovskite solar cells, the process of light absorption, electron hole pair generation, charge separation, and electricity generation persists, providing a continuous source of electrical power. Shockley-Quisser limit. This limit represents the quantity of electrical energy a solar cell can harvest from an incident photon. It is the maximum achievable efficiency of a solar cell in converting sunlight into electricity. The specific Shockley-Quisser limit for a perovskite solar cell depends on the band gap energy of the perovskite material used. The Shockley-Quisser limit functions as a reference point for evaluating the efficiency of solar technologies. In the case of perovskite solar cells, the band gap energies can vary based on their composition, leading to a corresponding change in the efficiency limit. The maximum Shockley-Quisser limit for a single junction solar cell is approximately 33.7%. Multiple junction solar cell has multiple semiconductors stacked on each other, which results in capturing a broader range of solar spectrum. The exact efficiency limit for multi-junction solar cells depends on the number of junctions and bandgap energies. Advantages of perovskite solar cells. Perovskite solar cells don't require heat and can be manufactured with much thinner layers, while silicon solar cells require heat during manufacturing greater than 1000 degrees Celsius and is comparatively thick. Perovskite solar cells can work with almost all visible wavelengths, resulting in more efficient transport, recombination, and extraction of charges than silicon cells. Perovskites can be adjusted to absorb distinct colors within the solar spectrum, resulting in increased power generation from the same device. This increases efficiency up to 30% and is done by combining it with other materials such as silicon to form hybrid structure, and this process is known as tandem device structure. Perovskite is also less expensive and its thin film structure requires 20 times less material, which are not supply limited. Thin film layer of perovskites are about 0.5 micron thick, while silicon layers are 200 micron thick. These thin films of perovskites are well suited for flexible substrates such as plastics and facilitate rapid charge separation. The photon energy which is lost during the conversion of light to electricity is less in perovskite solar cells as compared to other solar cells. Disadvantages. Some perovskite materials contain lead as a toxic element. There is the risk to people involved in the manufacturing of panels that use PSC technology, and there are also the problem for its disposal at the end life. Efforts to develop perovskite solar cells using lead-free, non-water soluble alternatives in trials have proven unsuccessful in achieving sufficient power conversion efficiencies. Perovskite materials are sensitive to moisture, oxygen, and heat. They can degrade over time, reducing the long-term stability and reliability of the solar cells. Gold is used as most common electrode material in perovskite solar cells to protect it from environmental conditions, but it hikes up the price. Producing uniform, high-performance perovskite material in a large-scale manufacturing environment is extremely difficult. The long-term reliability of perovskite solar cells in real-world conditions, including outdoor exposure, temperature fluctuations, and UV radiation, is still an active area of research. Challenges for perovskite-based cells. Stability of perovskite solar cells. Perovskite materials commonly employed in solar cells demonstrate instability upon exposure to oxygen, water, heat, and light. Beyond the external influences, certain investigations indicate that intrinsic characterization of perovskite materials, including ion mitigation and low defect formation energy, contribute substantially to the swift degradation of perovskite films. Presently, the perovskite solar cells demand a 25-year outdoor operational lifetime. However, this is not met by these cells. In addressing stability concerns, numerous approaches, including compositional engineering and interface engineering, has also been devised. An alternative approach involves passivating imperfections in the perovskite film through the introduction of various materials such as polymers, one-dimensional and two-dimensional materials, and fullerene derivatives. This strategy aims to enhance the overall stability of the device. The second challenge is toxicity of lead. Perovskite solar cells consist of lead-containing halide perovskites, which are selected for their outstanding optical and optoelectronic properties. However, the potential environmental hazard of lead leakage and associated human health risk necessitates the consideration of encapsulating and end-of-life recycling. The European Commission (EU) has imposed a restriction on the maximum allowable lead content in electrical and electronic equipment, limiting it to 0.1%, which is significantly lower than the current lead content required by PSC fabrication, which is about 5 to 10%. Efforts have been made to completely replace lead with other metals like tin, germanium, bismuth, and antimony. Nevertheless, PSCs based on these alternative based perovskites exhibit inferior performance. For example, while lead-based PSCs achieve photovoltaic conversion exceeding 25%, the highest PCE attained by tin-based PSC has attained only about 14%. These lower PCE values fall below the threshold, which is required for both single junction and tandem solar applications. Future advancements. Solar panels that generate electricity are commonly installed on building rooftops. Nevertheless, photovoltaic systems can seamlessly incorporated into the building structures BIPV, offering novel applications throughout the construction phase. BIPV involves incorporating panels into or as integral element of the building envelope, such as windows, skylights, exterior walls, or facades. This integration has been explored through three primary categories. The initial category encompasses semi-transparent perovskite solar cells studied for their potential, which is used in building windows and glass roofs. The second category involves the colorful PSCs for BIPU suitable for application in building fences, walls, and car power roofs. The third classification introduces PV windows, employing dual functional BIPUEs that integrate solar harvesting capabilities with electrochromic or thermochromic functionalities. Hydrogen production from water. Producing hydrogen from water has been viewed as a possible green approach. By applying an electric current to a suitable electrode, splitting of water into hydrogen and oxygen is achieved. Employing a high voltage PV electrolyzer and selecting an efficient electrocatalyst are imperative for effective water electrolysis. Equilibrium potential of 1.23 volts is required as a minimum energy for water splitting, where the practical operational potential can be varied between 1.5 and 2 volts. Instead of connecting several batteries due to the demand of such high operating voltages, connecting two individual PSC units is expected to meet the electrochemical potential required for water splitting, as PSCs typically display open circuit voltage values of more than 1.0 volts. Because of the distinctive features, which is their high power to weight ratio and improved resistance to gamma radiations. Perovskite solar cells are intriguing prospects for space applications. The potential of PSS for space applications is further increased by the fact that the instability problems that result from exposure to oxygen and moisture in the Earth's atmosphere do not exist in the space environment. Before a solar cell system is taken into consideration for space applications, it must meet the performance and stability requirements. It must undergo the characterization across a temperature range from 1 minus 150 degrees Celsius to 150 degrees Celsius. Solar cells in space may face erosion from solar winds and micrometeoroids. The PSS based devices should be designed in such a way that they can resist these erosions and degradation over time. Still, it has not been yet demonstrated practically whether perovskite-based tandem devices are feasible for use in space applications. To evaluate the effects of subjecting PSS to UV radiation, temperature changes, and space vacuum, more research is required. Given that the UV intensity in space application is considerably higher than in AM0 conditions, its significance is notably heightened. Space probes, landers, and rovers exploring the other planets and celestial bodies can benefit from perovskite solar cells. Their high energy conversion efficiency can help extend the mission duration and improve scientific data collection. Future space stations, lunar bases, and Mars habitats may utilize perovskite solar cells to generate electricity. In the future, perovskite solar cells may play a role in interstellar missions, harnessing energy from distant stars for long duration, high velocity missions. Now we'll discuss about semiconductors. Semiconductors are materials that have electrical properties between those of conductors and insulators. They're widely used in the fabrication of electronic devices such as diodes, transistors. They then perform various functions such as amplification, switching, and energy conversion. The behavior of semiconductors depend on the movement of charge carriers such as holes and electrons within the crystal structure. By introducing impurities, also called doping, the number and type of charge carriers can be controlled, creating different regions such as p-type semiconductors and n-type semiconductors. Semiconductor materials. There are different semiconductor materials which are widely used. The choice of the semiconductor material depends upon the specific requirement of the application. Silicon. Silicon is used as a semiconductor material as it is easily available, making about 28% of Earth's crust and is inexpensive. Its structure is the contributing factor making it useful in electronic device as it has stable crystal structure and forms thin layer of silicon dioxide on the device surface which protects the device from corrosion. It has a moderate band gap, helping prevent current leakage and can be easily doped. Silicon is also compatible with other materials such as nitrides and oxides that make different electronic components such as transistors, diodes, and integrated circuits. Gallium arsenide. It is also used as semiconductor material due to its high electron mobility, which means that it can operate at higher frequencies and with less power consumption. Ga is more resistant to radiation and heat. Therefore, it is used in communication systems and sensors, and it has a direct band gap, which means that it can emit light more efficiently than silicon. This makes gallium arsenide suitable for use in light-emitting devices like LEDs. However, the fabrication of gallium arsenide is relatively challenging and leads to increased cost. Gallium nitride. This type of semiconductor material is widely used in microwave transistors where high temperature and powers are required. This property of operating at high temperature and voltage reduces the need for cooling systems and protection. The performance and cost of a device can be optimized by gallium nitride as it can be grown to different substances such as sapphire and silicon carbide. Gallium nitride was the key material for inventing blue LEDs, which further led to the development of white LEDs and Blu-ray discs. However, achieving p-type regions through doping presents a notable difficulty in case of gallium nitride. Preparation of semiconductor material. The first step is material selection. When choosing a material, physical and chemical properties are carefully considered. These properties include the band gap, which determines the energy required for material conductivity, carrier concentration influencing current flow and resistance, mobility measuring the speed of charge carriers, and thermal conductivity. Reliability of a material is also taken into account. This indicates the material's resilience against diverse stresses and degradation mechanisms, including temperature, humidity, corrosion, and radiation. These aspects can impact the performance, lifespan, and safety of the semiconductor device, potentially leading to failures or malfunctions. The second step is crystal growth. Many semiconductor materials are grown as single crystals to ensure uniformity and high quality electrical properties. The crystal growth process typically involves one of the following methods. The first method used for crystal growth is Turoleski method. In Turoleski method, a seed crystal is attached to a holder and is inserted into a crucible of molten material and is then slowly pulled from the melt. This results in a crystal growth by solidification of molten material on the seed crystal surface, and orientation of growing material is identical to those of seed crystal. Thus, a cylindrical crystal bar, also known as bowl, is formed. It is then rotated at several revolutions per minute. The seed crystal is then slowly pulled upward, and as it moves through the melt and solidifies into a larger single crystal, and the whole process is indicated in this diagram given below. The second method for crystal growth is Bridgman-Stock-Barger method. In this process, a small crystal of the material to be grown is positioned at the bottom of the vertical tube. A seed crystal is positioned in the intended crystallographic direction. The tube is then placed in a high temperature furnace and the material is heated until it melts in the lower part of the tube. A temperature gradient is established within the tube, with the lower region being at higher temperature than the upper region. The temperature gradient is carefully controlled to facilitate the controlled growth of the crystal. As the temperature gradient is upheld, the seed crystal is gradually raised to the molten material. The controlled cooling and slow lifting process allows for materials to solidify and grow as a single crystal. The speed at which the seed crystal is pulled through the temperature gradient impacts the ultimate size, quality, and properties of the resulting crystal. This process is illustrated in this diagram. Then comes wafer formation. After the growth of crystal, the material is cut into slender flat wafers. These wafers typically are made of silicon and they serve as a substrate for semiconductor device fabrication. The wafers must be free of defects and possess a high degree of crystallographic orientation. Fabrication processes. Semiconductor wafers go through a series of fabrication processes that create the intricate patterns and structure needed for the construction of electronic components. These processes include photolithography, etching, ion implantation, and the deposition of materials like metal and dielectrics. These steps create transistors, diodes, and other components. The fourth step is device integration. The prepared wafers with electronic components undergo multiple layers of integration. The layers consist of different semiconductor materials and insulators that are combined to create integrated circuits or discrete devices. The design and layout of these layers depend upon the intended application-specific design requirement. Annealing and heat treatment. Heat treatment processes such as annealing are often used to activate the dopants, repair crystal damage, and improve the electrical characteristics of the semiconductor. Annealing helps in the redistribution of dopants and can relieve stress in crystal lattice. Packaging. Semiconductor devices are encapsulated in protective packages such as ceramic, plastic, or material to shield them from environmental factors and provide electrical connections. Packaging also plays a crucial role in mechanical protection. And the last step is assembly. Depending on the application, semiconductor devices can be assembled into larger electronic systems. This can involve mounting devices on printed circuit boards, connecting to other components, and integrating into complete electronic products. The preparation of a semiconductor material is a highly controlled and specialized process, often conducted in clean room environment to prevent contaminations. Types of semiconductors. The two types of semiconductors, intrinsic semiconductors and extrinsic semiconductors. The intrinsic semiconductors are pure materials that have no impurities or dopants, therefore they're also referred to as undoped. Intrinsic semiconductors manifest the inherent characteristics of semiconductor materials, excluding properties and dopants. They have a balanced number of electrons and holes, which are the charge carriers in semiconductors. Holes represent the absence of electrons in the valence band and function as positive charge carriers. Intrinsic semiconductors have low conductivity at room temperature as the electrons are tightly bound to the atom and they need a lot of energy to jump to the conduction band. Extrinsic semiconductors. These are materials that are doped with other elements to modify their conductivity and properties. These semiconductors are alternatively termed as impurity semiconductors or doped semiconductors. In this, electron density is not equal to the density of holes. Extrinsic semiconductors exhibit elevated electrical conductivity to the process of doping. Depending on the type of dopant, extrinsic semiconductors can be divided further into two types, p-type semiconductors and n-type semiconductors. In n-type semiconductors, pentavalent atoms are doped such as phosphorus, arsenic, or antimony. These elements possess 5 valence electrons, one more than the atoms in their semiconductor. Upon their incorporation into the semiconductor lattice, they contribute their additional electrons to the conduction band, resulting in an excess of negative charge carriers. N-type semiconductors have high conductivity because the electrons can move easily. Therefore, they're also termed as N, which stands for negative or electron type semiconductors. In this, the major carriers are electrons. P-type semiconductors. These semiconductors are doped with trivalent elements such as boron, aluminium, or indium, and these elements constitute 3 valence electrons, one less than the semiconductor atom. When they are added to the semiconductor lattice, they accept an electron from the valence band, creating a surplus of positive charge carriers. Therefore, the majority charge carriers in P-type semiconductors are holes, which represent the absence of electron. Working of a semiconductor. PN junction. Many substance semiconductor devices are built around PN junction. These are interfaces between P-type semiconductor and N-type semiconductor. At the junction, there is a region where the semiconductor material transitions from P-type to N-type. Electron hole pairs. In P-type semiconductor, there is an abundance of holes which are positively charged carriers due to the presence of dopants like boron. In the N-type semiconductor, there is an excess of electrons due to dopants like phosphorus. Electron movement. When a voltage is applied to the PN junction biased, electrons from N type move towards P type and holes from P side move towards the N side. This movement of charge carriers is influenced by electric field at the junction, barrier formation. As electrons and holes move across the junction, they undergo recombination. This recombination creates a depletion region or a barrier at the junction where there are no charge carriers. In the absence of applied bias, this area functions as a barrier to the flow of electrical current. There are two biases, forward bias and reverse bias. When a forward bias voltage is applied, it reduces the barrier, allowing the electron hole pairs to recombine more easily. This results in the flow of electrical current across the junction. Reverse bias. However, when reverse bias voltage is applied, it widens the depletion region, increasing the barrier. This prevents the flow of electrical current and the junction acts as an insulator. As we can see in the diagram indicated, we can see both forward bias and reverse bias PN junction. The depletion region shown in reverse biasing is clearly more wide as compared to the depletion region which is present in forward biasing. The future advancements of semiconductors, AI chips. AI chips, also known as artificial intelligence chips or AI accelerators, are specialized semiconductor devices crafted to accelerate artificial intelligence and machine learning workloads. This recent generation of microprocessors is crafted to enhance the processing speed of AI tasks while consuming minimal power. These AI chips are compact, cost effective, energy efficient, and emit minimal heat. Semiconductor companies are incorporating AI into manufacturing workflows to optimize operations and elevate product quality. The integration of AI in chip design improves productivity by reducing design time, cutting cost, minimizing resource requirements, and significantly accelerating time to the market. Retail companies which rely on technological infrastructure stand to gain from these advancements. As the efficiency of chip design and manufacturing advances, retail enterprises can more regularly enhance their technological infrastructure, resulting in improved operational efficiency and high customer service. Additionally, AI augmented chip designs have found applications in real life scenarios, including autonomous vehicles, facial recognition, and 5G mobile devices. Facial recognition has the potential to improve in store security and personalized marketing, while 5G can facilitate immersive technologies like augmented reality and virtual reality. However, the integration of AI into chip design possesses challenges, including rising costs and risk in manufacturing processes, extended development timeframes, and constraints on engineering resources. One example of AI chips are neuromorphic chips. The neuromorphic devices exhibit remarkable effectiveness in receiving and responding to the data from the environment. When coupled with organic materials, these devices become compatible with the human body. In the future, neuromorphic devices hold the potential to enhance drug delivery system by responding to changes in body conditions such as insulin and glucose levels. Their exceptional responsiveness will enable them to administer a drug upon detecting changes in bodily conditions such as varying insulin and glucose level. Due to their low energy consumption, neuromorphic computing is well suited for edge computing, particularly in the outskirts of a network that connects to a cloud platform. In case of driverless cars, the cars which do not need any driver, neuromorphic computing could enhance their responsiveness to surrounding, making them more safe and more adaptable to diverse environments. In the absence of a reliable internet connection, a system utilizing neuromorphic computing could assume control of these vehicles. Rebellious is a South Korean startup that offers domain specific AI processors. The startup builds AI accelerators by bridging silicon architectures and deep learning algorithms. It employs silicon kernels to modify the processor architecture, making it compatible with intricate deep learning algorithms. In this manner, this dedicated AI hardware expedites machine learning computations, enhances performance, and diminishes deployment cost. 5G technology. With the escalating demand for data, 5G networks may employ higher frequency bands like sub-terahertz and terahertz ranges to attain elevated data rates and reduce latency. However, these bands pose significant challenges for semiconductor devices such as high path loss, atmospheric absorption, and thermal noise. Therefore, new semiconductor material and technologies such as graphene, carbon nanotubes, and 2D materials will be needed to overcome the challenges and enable effective and reliable sub-terahertz and terahertz communication. Massive MIMO and beamforming. Massive input and massive output, also termed as MIMO and beamforming, are key technologies for 5G networks as they can enhance the spectral efficiency, coverage, and reliability of wireless communications. These technologies require a large number of antennas and RF components, which increase the complexity, cost, and power consumption of a system. Therefore, new semiconductor devices such as gallium nitride and silicon germanide will be needed to integrate and optimize the RF front end and enable scalable and energy efficient massive MIMO and beamforming systems. Edge computing and AI. Edge computing and artificial intelligence and emerging technologies that enhance the performance and functionality of 5G networks by enabling low latency, high reliability, and context aware applications and services. These technologies require high performance, low power computing, and processing capabilities which are challenging to achieve with conventional semiconductor devices. Therefore, new semiconductor solutions such as neuromorphic chips, quantum dots, and AI accelerators will be needed to enable edge computing and AI for 5G networks. Conclusion. In conclusion of this article, the advanced material chemistry in electronics is a rapidly evolving field that has the potential to revolutionize various applications such as energy storage, sensing, communication, and computing. By designing and synthesizing novel materials with tailored properties like graphene, perovskites, and nanowires, researchers can create devices that are more efficient, flexible, scalable, and multifunctional. Advanced material chemistry is a cutting edge field that aims at producing innovative ideas and devices. However, there are also many challenges and limitations that are needed to be addressed, such as synthesis methods, stability, compatibility, and integration. Therefore, further research and collaborations are needed to explore the full potential of advanced material chemistry in electronics and its impact on society and environment. In developing new device challenges such as safety, capacity, and cost are also a major hindrance. Semiconductors are the backbone of modern electronics and can be manipulated by nanostructuring the device for achieving desired functionalities. Advanced material chemistry offers exciting opportunities for design, optimization, and fabrication of electronic devices to meet the demand of the 21st century and beyond. These are some of the citations for this article. Thank you for your precious time.